In this video, we will talk about graphing sine and cosine waves that have a vertical shift. This means the entire wave will be shifted either up or down on the coordinate plane. In addition to a vertical shift, the three examples that we'll talk about in this video could also have a change in amplitude, a change in their fundamental period, as well as the vertical shift. But regardless of the properties of the wave, the graph of a sine wave will be based on a shape that looks like this, and the graph of any cosine wave will be based on a shape that looks like this. Let's begin. Our first example will be to draw the graph of y equals the cosine of x plus 2. This equation involves a cosine function, so it will be based on a wave that looks like this. The only change from y equals the cosine of x to y equals the cosine of x plus 2, you can see, is that there is a plus 2 term at the end. And when there is a value added or subtracted to the end of a trig equation, that results in a vertical shift. If the value at the end that is added is positive, that's a vertical shift up. And so in this case, because there's a plus 2 at the end of this equation, I'm going to shift the graph of y equals the cosine of x up 2 units on the coordinate plane. This graph will look exactly like y equals the cosine of x, except it will be shifted up 2 units. A good place to start after you identify that there's a vertical shift of 2 units is to draw a dotted line 2 units above the x-axis, 2 units above the x-axis. And that dotted line technically is not part of the graph, but it will serve as the vertical center as I draw the graph. I'm going to draw the same shape that starts at the top of the amplitude, gets to the bottom of the amplitude halfway through the graph, and rises to the top of the amplitude after one cycle of the wave, but it's all going to be based on this dotted line. The beginning end of the graph will be based on this dotted line. This entire shape will be drawn after 2 pi radians on the x-axis. So one cycle of the graph will begin at 0 and one will end at 2 pi. In the graph of y equals the cosine of x, it starts 1 unit above the x-axis, but because this is shifted 2 units up, it's going to start 1 unit above this dotted line that I've drawn, 2 units above the x-axis. One cycle of the graph will start at the point 0, 3. By the time that it gets to the middle of one cycle of the graph, at pi radians, in the graph of y equals the cosine of x, it will be at the bottom of its amplitude, 1 unit below the x-axis, in the case of y equals the cosine of x, but on this graph it will be 1 unit below the dotted line, that is 2 units above the x-axis. And then the graph of y equals the cosine of x returns to where it started, 1 unit above the x-axis in y equals cosine of x, and that's at 2 pi radians, but in our graph at 2 pi radians it will be 1 unit above the dotted line, which is 2 units above the x-axis. So the 3 points that I have drawn on the big coordinate plane correspond to the 3 points that I'm outlining in blue in the graph of y equals the cosine of x. It's also important to realize that in the graph of y equals the cosine of x, a fourth of the way through the graph, it crosses the x-axis or goes through its vertical middle, vertical center, and 3/4 of the way through the graph of cosine of x, it also crosses the x-axis. On our graph, a fourth of the way it will cross that dotted line that we've drawn, and 3/4 of the way through one cycle of the graph, it will also cross that dotted line. I'll go ahead and connect the 5 points that I've drawn with a smooth curve to form one cycle of the graph of y equals the cosine of x plus 2. What I have on the screen in red is one cycle of the graph of y equals the cosine of x plus 2. Now, of course, this will repeat itself infinitely to the left and to the right and I'll go ahead and fill up the coordinate plane that I've been given by repeating this graph as much as I can until I get to the end of the coordinate plane that I've been provided with. On the screen right now is the graph of y equals the cosine of x plus 2. It's a cosine wave that has been shifted up 2 units because of the term plus 2 that we see at the end of the equation. Our second example will include not only a vertical shift, but also a change in amplitude and a change in the fundamental period of the wave. We'll graph y equals 2 sine of 1/2 x minus 1. This is a sine wave, so it will be based on the graph of y equals the sine of x, but we'll be adapting this general shape based on the amplitude, fundamental period, and vertical shift we identify. So first, let's identify those 3 properties. First, the amplitude. The amplitude is based on the coefficient on the sine function, which in this case is a 2, and the formula for the amplitude is the absolute value of that number. And the absolute value of 2 is 2. So the sine wave that we'll draw on this graph will have an amplitude of 2. Next, let's identify the fundamental period of this wave. The fundamental period comes from the coefficient on x, which is often abbreviated with a value or as b. The amplitude is a. We'll call the coefficient on x a value of b, and the fundamental period, the number of units on the x-axis it takes to complete one cycle of the graph, comes from 2 pi over b. So in this case, that would be 2 pi over 1/2. And 2 pi divided by 1/2, 2 pi divided by a fraction is the same thing as 2 pi times the reciprocal of the fraction, 2 pi times 2, which is 4 pi. So the fundamental period of this wave will be 4 pi radians. It will take 4 pi units along the x-axis to complete one cycle of this graph. Finally, the vertical shift. The vertical shift comes from the number that's added or subtracted at the end of the equation, which in this case, there's a -1 there. And because that's a minus sign, the vertical shift will be 1 unit down. This will be a vertical shift of 1 unit down. Our entire wave will be shifted 1 unit down from the x-axis. And that's a good place to begin actually drawing the graph. Since there's a vertical shift of 1 unit down, I'm going to begin by drawing a dotted line 1 unit below the x-axis. And moving forward, everything I do to draw this graph will be based on the graph having a vertical center at that dotted line. The graph of y equals the sine of x begins right on the x-axis. This graph will begin right on the dotted line that I've drawn. And when I say begin, what I mean is that one cycle of the graph will begin there. This graph extends to the left and right indefinitely, but I'll start by drawing one cycle of the graph, which, when it comes to the sine, begins right in the middle, right in the vertical middle of the graph. Then the graph moves up to the top of its amplitude before moving down to the center, its vertical center, halfway through the graph. It will be at the top of its amplitude a fourth of the way through one cycle of the graph. It will reach its vertical center again halfway through the graph before going to the bottom of the amplitude 3/4 of the way through the wave, and then returning to the middle after one cycle is complete. In this case, I've already drawn a blue dot on the big coordinate plane where one cycle begins, and because the fundamental period is 4 pi, one cycle will end 4 pi units over on the x-axis. Remember that halfway through one cycle of the graph, in our case halfway between 0 and 4 pi, it will also be right in the middle. Halfway between 0 and 4 pi is 2 pi, so the graph will return to its middle after 2 pi radians. The graph of y equals the sine of x after starting at the origin rises to the top of its amplitude and reaches it a fourth of the way through one cycle of the graph. In this case, a fourth of the way from 0 to 4 pi would be 1 pi. So that's when the graph is going to get to the top of its amplitude. And remember, its amplitude here is 2. So from this dotted line, by the time I go from the beginning of one cycle to a fourth of the way through the wave at pi radians, it will be 2 units above that center. 2 units above the dotted line. 2 units above the dotted line because the amplitude is 2. So it's going to begin at the point 0, -1. It's going to rise to the top of its amplitude after pi radians, a fourth of the way from 0 to 4 pi, before it turns around and goes back down to the dotted line halfway through one cycle of the graph, halfway between 0 and 4 pi at 2 pi. After it reaches its halfway point, now it's going to go down to the bottom of its amplitude, and it's going to reach its lowest point 3/4 of the way through one cycle of the graph. 3/4 of the way from 0 to 4 pi would be 3 pi. So at 3 pi radians, it's going to be at the bottom of its amplitude. And remember, the amplitude is 2, so that will be 2 units not below the x-axis, but 2 units below the dotted line that I started with, because this graph is vertically shifted 1 unit down. Continuing the wave to reach that low point before turning around and continuing back to the dotted line where it started after 4 pi radians. What you see on the screen now is one cycle of the graph of y equals 2 sine 1/2 x minus 1. We'll go ahead and continue drawing this curve to fill up the coordinate plane that I've been given, and basically you're just going to repeat this same wave that you have for as much of a coordinate plane that you've been given. And in this case, that's not too much. I can get to a high point as I move to the right before turning around, and as I go to the left I get down to a low point before turning around just barely. So on the coordinate plane given, what you see on the screen now is the graph of y equals 2 sine 1/2 x minus 1. The final example will be another sine wave, y equals negative sine of 2x plus 3. Like our other examples, we'll begin by identifying the properties of this wave. First, the amplitude. The amplitude comes from the coefficient on the sine function, and in this case there's not a number written. It's understood to be a 1, but it's actually -1. The value of a in this equation is -1. Now the amplitude is the absolute value of a. In this case, that would be the absolute value of -1, or just 1. We'll talk about how that negative affects the graph when we get to the point of actually drawing the graph, but the amplitude itself is +1. The fundamental period, the number of units it takes to complete one cycle of the graph. That comes from the value of b, the coefficient on x. The formula to determine the fundamental period is 2 pi over b. So in this case, that will be 2 pi over that value of b, which is 2, which will reduce to just a pi. The fundamental period, the number of units along the x-axis that it will take to complete one cycle of this graph, is pi radians. And finally, the vertical shift. The vertical shift comes from the value of c, the number added or subtracted at the end. In this case, it's +3. So that means that there will be a vertical shift of 3 units. Because it's +3, it will be shifted 3 units up. And that's where I'll begin the graph. Because there's a vertical shift 3 units up, I'll start by putting a dotted line 3 units above the x-axis. This will serve as the vertical center of the graph that I draw. And before I start to actually draw this graph, let's remember that when there's a minus sign in front of the sine curve, or any function for that matter, that results in a rotation about the x-axis. Basically, it takes the graph and flips it upside down. So this sine wave, instead of looking like what you see on the screen now in the top right-hand corner, it will begin at the same place, but instead of going up, it will go down. And in the second half of the graph, instead of going down, it will go up to the top of its amplitude. So this curve will have a general shape that begins in the middle of the graph, goes down to the bottom of its amplitude, and then after halfway through the graph, it will be back at the center before going up to the top of its amplitude and returning to where it started after one fundamental period. In this case, so we'll begin right on the dotted line, but instead of rising to the top of the amplitude, I'm immediately going to start drawing this curve going down. And this is, again, because there's a negative in front of the sine. Since the fundamental period is pi, one cycle of this graph will end after pi radians, and again, a sine wave returns to its center halfway through its graph, halfway through one cycle of its graph, and a fourth of the way, it will be at the bottom of its amplitude. And its amplitude, again, is 1, so halfway between 0 and pi over 2, it will be at the bottom of its amplitude. And since its amplitude is only a 1, this curve will only fall 1 unit before returning back to its vertical center. For the second half of one cycle of the wave, it will rise to the top of its amplitude. Halfway between pi over 2 and pi would be 3 pi over 4, and on this coordinate plane, that would be this point. So I'll rise to that point before falling back to the dotted line, and I've now completed one cycle of the wave, y equals negative sine 2x plus 3. This purple wave that I've drawn on the coordinate plane has an amplitude of 1. It rises 1 unit above the dotted line and falls 1 unit below the dotted line. It has a fundamental period of pi because I've completed one cycle of the graph between 0 and pi radians. And it has a vertical shift of 3. The whole thing is shifted up 3 units. So I've completed one cycle of the graph here. Now, the coordinate plane that is on the screen is a lot bigger than this single cycle, so I'll basically repeat this shape to draw the wave every pi radians. I can draw another complete cycle of the wave between pi and 2 pi. I can fall to the bottom of the amplitude, return to the dotted line halfway through the cycle, rise to the top of the amplitude, and return to the dotted line after 2 pi radians. I can't quite draw another complete cycle of this wave, but I will fill up the coordinate plane that you see on the screen by drawing as much of it as I can, both to the left and to the right. On the screen now is the coordinate plane that I've been given completely filled up with the graph of y equals negative 1 sine of 2x plus 3.